So question 22. A and B are 0.25 meters apart in an electric field of 1,000. In an electric field, if 1,000 joules of work are required to move a 4 coulomb charge from A to B, what is the electric field strength? So here you find yourself one of the work done formulas. Now let me see on our help sheet. Work done is equal to E. Let's see. EQD. Yep, work done is equal to EQD. Beautiful. Why did I know that I needed that? Because it gave me, I needed to find E, it gave me the work done, it gave me the separation, and it gave me the charge. It gave me everything I needed to slot perfectly into that formula, so that's what I did. Alright, super easy, work it out. The field strength is 1,000 volts per meter. Okay? Easy question, just wanted to point out the use of that formula. In example 23, okay, in the electron gun of a synchrotron, again, you should have watched the video on synchrotrons by now. Electrons are accelerated by a voltage of 5,000 volts. Which one of the following best gives the speed of the electrons? Okay, so if you accelerate an electron through a potential difference, it picks up that potential difference in energy. So it'll pick up 5,000 electron volts. Okay, so what is an electron volt? Well, an electron volt is a measure of energy, remember? Equivalent to joules, as in electron volt, I'd go 5,000 EV, which would be 5,000 times 1.6 by 10 to the negative 19, and that will give me how much energy this electron picked up in joules. Now I have to have it in joules because this formula won't work if you chuck electron volts in it. Okay, so solve for V. Again, this should be on your help sheet. Okay, maybe even more than once because you use this a bit in energy and in projectile motion, and I think now you're using it as well in electric fields. So you might want it in a couple of places to make sure if you're sitting an exam that it's kind of there to jog your memory on what you're supposed to use. So once you know the energy that the electron has picked up, solve for its velocity, and you end up with usually really high velocities, 4.2 by 10 to the 7 meters per second. Okay, so it doesn't actually take much to accelerate an electron to a staggering, fast speed. Right in here, you know, from our study of general relativity, you would find there would be some serious, some decent at least, Lorentz factor effects on your electron. Would be significantly heavier, it's time dilation, length contraction, all of that stuff would be happening at these speeds. Anyway, moving on. Okay. Now, this was an interesting question. Again, another one. This one references Millikan's experiment. I'm really glad that you went and paused the video and went and watched some Millikan stuff when I said you should. The diagram shows the trajectory of a particle with a charge Q and mass M when fired horizontally into a vacuum chamber, where it falls under the influence of gravity. Okay? Vacuum chamber, meaning it's going to accelerate down. Okay? It's not going to hit terminal velocity in any way. Alright? Because there's nothing there. No friction in there. Okay? So it enters at 10 centimeters above. Okay? And gravity grabs it and bang, it hits the ground. Okay? So the horizontal distance d travelled by the particle is recorded. Okay? So whatever energy it was given, in there you go. Now, what did they do? Well, the horizontal distance d travelled by the particle is recorded. The experiment is repeated with a uniform vertical electric field applied such that the particle travels the same horizontal distance but lands at the top plate rather than the bottom plate. Okay? So, what is the magnitude of the electric field that causes this? Now, you've got to say to yourself, okay, and these are the answers. Here, 2 mg over q, 2 mgq, 2 mgq. Okay, there's a lot of mgqs in here. So you've got to say to yourself, okay, so where am I going to get? This question is 2019, New South Wales. Okay, this was last year's question. So this is not like one of those weird questions from the 60s that you'll never see again. But here, your counterparts in New South Wales were looking at this question last year. So take it seriously. It may be important. Now, you know that the force that this particle is under in the first part of this experiment is the force of gravity. The force of gravity, F equals mg. F equals mg. Now, for the particle to, instead of land here, so it had the same exact horizontal distance covered before it actually made contact. What I did was I asked myself, what if the particle just never fell and just shot across the whole way? That would mean that the electric field was equal to exactly mg. So the force from the electric field had to be exactly mg. So then I thought, well, that means for it to land precisely the same distance away from the entry point that it did below, that it thinks that gravity's going the other way. So as far as it knows, the force of gravity that it's experiencing is just the same, except I fell the other way, okay? So for that to be true, mg, if the particle experienced a force mg equal to mg, it would have just shot across. So therefore, the field had to be not mg the other way, but 2mg. It had to overcome gravity just to have it horizontal, and then double it to make it land at the other end, or on the other side. So hopefully that wasn't like the most ridiculous explanation ever. So what I did was, I had a look at it, and I thought, okay, F equals QE, alright, F equals QE, and to figure out what the electric field is to cause this motion, the force due to the electric field had to be the same as the force of 2 gravities. Okay, so 2 mg's. Okay, that is how I kind of logicked out the whole why it would land exactly the same distance out from the beginning, but on the other side, on the other plane. Okay, so hopefully that kind of makes sense. Because if you can see why I've done that, then equating the two, so this is the force experienced was double gravity, basically. Now remember, it's a particle, so it has a mass m, it is falling under gravity, all of this stuff is nice and consistent. And then now solve for E. Solve for E equals 2mg over q, and 2mg over q is the correct answer there, and using all of the variables that were required. Okay, so that was question 24. I didn't do this one or this one. Here, I don't really like that question. Don't worry about it too much. That's another one of those 60s questions. Here we go, potentials and fields. Okay. This is the one I was kind of talking about earlier when we were talking about plates and wires acting as plates. Okay. So you can see here that we have 3 different wires of equal length and uniform cross-section are connected to a battery as shown below. Alright, so here, this wire has a resistance of 2R ohm, and this is 2R ohm, and this is 1R ohm. And from your understanding of electricity, the current, this is the positive terminal, so we have potential, maximum potential at this end, okay, and 0 potential when we get down. It even says 0 potential, okay, so you know which way it's going, okay? Which of the graphs below represents the relationship between the potential, so the voltage, and the distance around the circuit, all right? So the voltage and the distance around the circuit. Now we've got here E. It says E is the correct answer. We'll have a look at this. Now I'm assuming you've actually already attempted this question, and if you're looking at this, then you didn't understand the answer. Okay, so if it's saying potential what we want to look at is between the potential distance and the distance around the circuit. So that's what we're asking for. The potential difference, the voltage drop, and the distance around the circuit. Okay, so the potential drop, as you should know, is whatever the voltage is here, for every 2 volts that are dropped here, 1 volt will be dropped here and 2 volts will be dropped here, okay? As per V equals IR, all right? The current will be the same everywhere, so you don't have to worry about that, okay? So the potential drop will be high here, less here, bit higher here, and at the bottom it'll be 0, okay? So in other words, you'll start with the most potential at K, it'll drop uniformly here at some rate, it'll drop uniformly here at less of a rate because it's not consuming as much voltage, and then back up at a higher rate, the same rate as this side here. So that's why when you look at E, you can see that the rate of drop as it moves across KLMN, the rate of drop is high, less, high, 0 at the end. That's really important, okay? Here, this graph goes the wrong way, this graph goes the wrong way. This graph just assumes that the voltage is nice consistent the whole way through. This, I don't know. This one says there is no drop in voltage between K and L. Yeah, no drop in voltage? How? Yeah, because if that's volts, or potential difference and distance around, no, it's dropping a consistent amount. I don't know. I don't like that one. It's just saying that there's no... Yeah. Oh, I'm going to cut that bit out of the video. All right. Now, moving on. Question 29. Which of the graphs A to H below represents the relationship between the current... Wait a second. Oh, yeah. These ones are completely wrong. I just realised. Because you end up with the same voltage at the other end, at N. Here, you end up with the same voltage at N. So in other words, this implies that there is a voltage at N, okay? There is no voltage at N. It's at 0, okay? So there you go, sorry. Now, go back to A. 29. Which of the graphs the relation between the current and the distance around the circuit? It is a series circuit, isn't it? So the current represents the flow of electrons. So they're losing their energy as they go, but they're still there, okay? They're there all the way around. So that's why A has to be the correct answer. There is no variance of the current around the circuit. It's the same everywhere, okay? And the last one, which of the graphs shows the relationship between the electric field around and the distance... Oh, so let me just read it properly. Which of the graphs A to H below represents the relationship between an electric field around and the distance of the circuit? So what they mean there is the electric field around the wire. So you can see the electric field is voltage, divided by distance. Now the distance for this is, it's the wire itself. There is no real distance, but you know that when you run a current through, you create an electric field. Those charges are creating an electric field. And so electric field G, this is related to the voltage dropped in each section, because you can see electric field is calculated by V over D. All right, so more voltage, stronger electric field. So that is why when we go to the correct answer to this is G, where the field is strong, uniformly along the wire, as those two sets of plates. A bit less in the other one, and then more again in the other one, okay? That's the opposite of what actually happens. All right. All right, question 31. Let's see, basic concepts, fields. All right, yeah, this is just more vector stuff, but it goes back to E equals KQ on R squared. All right, so you can see in my drawing of this, I've taken notice that this particle here is another one of these particles. It's asking for the field strength, so it's not reliant on whether this is a positive particle or a negative particle or something else. But we do follow the rule of when it's an empty space, we imagine a small positive charge at that spot to see what the field will be doing, okay? And that would allow us to then draw field lines or draw vectors. And so in this case, we're going to use vectors. You can see that if this is a small positive charge, then this is a positive charge and it will feel a force in that direction directly from this guy here. Same, if this is a small positive, it wants to be here, so it's going to feel a force in this direction. Okay, now, notice that this vector is much bigger than this vector, all right, because I've taken also notice of that this charge is twice the size of this charge, okay? So, this is also another equilateral triangle, so I chucked in a bunch of other things that I know are important. For example, 60 degrees, all right? Bisect the line, that will be 30 degrees, and this will cut this exactly in half, so 1.5, 1.5. All right, so all these little facts that I know that are ready in case I need them. All right, so it asks, find the magnitude of total field strength at the vertex of this equilateral triangle. So it asks for the magnitude, so you don't need an angle, which is great. Work out what the field strength is at this distance away from this charge and at this distance away from this charge, okay? And the way you do that is kq over r squared, which is just the standard formula you've used several times already. For 1, in light blue, I do the calculation and I actually have all of the values required. This is plus 2 nanocoulombs and this is -4 nanocoulombs, so this is an actual number, it's not just a general value. And for the first calculation, 20,000 newtons per coulomb by doing that calculation. So that vector there is 20,000 newtons per coulomb. All right, that's the electric field strength there. For this one, I did it in green, so you can see that's in green, 40,000. Then I join my vectors together, all right, vector sums, and what I do is, from there, I make the discovery that this is actually a right triangle. Okay, that's 60 degrees, that's 30 degrees, and this is just a bunch of like angle triangle facts. So I wonder if you could use the parallelogram. Yeah, you probably could actually. If you used your parallelogram method, that value of that vector and that vector, so you probably know that, let's see, that's 30 degrees, that's 30 degrees, all right, so it's 60. Yeah, okay, so you can actually show that is, yeah. Good, so that would give us this vector here, which is this vector here, okay? And that gives us, yeah, that's that there. Okay, beautiful. Nice, yeah, so you do get that 90-degree triangle, okay? So lovely. That's actually, I really like that method of adding vectors. All right, fantastic. So the idea that once you make the discovery that's a 90-degree triangle means you just like drizzle a little bit of Pythagoras on there, and you can find what the magnitude of that vector is, which is right here, 40,000. Now, hopefully you've noticed that that triangle, you have the hypotenuse and you have that value there, but you need to find the other short value, which changes the way you use Pythagoras to the minus version. 40,000 squared, take 20,000 squared, and you get 34,641 newtons per coulomb. And then it asks, I think does this one ask for the angle later on? No, it does not. Okay, cool, easy. All right, question 33. Question 33, I just did question 33 because I haven't seen one like this before, where in 33, this charge is half the charge of this one, okay? So the field between them is a typical, here, it's a typical field like this, right? It's one of these, except where one of the charges is stronger than the other, okay? You need to show the difference. You don't show it by drawing bigger circles and smaller circles. You show it by drawing more or less field lines. So as you can see, The stronger charge has a lot more field lines. The weaker charge has less. And even that sort of bulge that you get that is normal through the middle is more pronounced towards the other charge. Just if you've seen that once, then you'll never not be able to do it. That's just a pretty easy question. I just want to make sure, since I'd never seen that before, a question like that before, it'd be great for you to know it. Okay, all right. God, how many questions did I do? All right. The three equal size charges, A, B, and C, are placed as in the diagram below. A and B are positively charged, while C is negatively charged. So always take a mental note of which way everybody's pushing. All right, these guys are pushing this way, and this guy's pulling in this way and this way. All right, cool. So you know which way everything's kind of going. It asks. Okay, they are equally charged. They're placed in those positions. This one's 2 centimeters away from this one, and this one's 1.73 centimeters from this one, which means there's a bigger push this way than there is this way. There's a bigger pull this way than there is a push this way because these ones are a little closer. Okay, charge A exerts a force of 4 micronewtons on charge B. So A and B are pushing this way with 4 micronewtons of force. Okay, so you know that. Now, this is an interesting question because it doesn't give you what Q is, all right? It doesn't give you seemingly enough information. But because all the Q's are the same, what I did was I just figured out what the force was between these two in terms of Q. But because the Q's were the same, I just turned them into Q squared. All right, just for neatness, I guess. But I know how far apart they are, and I know what force they exert on each other. So I can figure out exactly, well, if I do that there, I can understand someone as a student maybe getting there and not really realizing where to go next, but kind of maybe doing the same thing for the other two charges, knowing what their separation is. Now, if you've got a good sort of maths head on you, you might notice these two are the same value. And if they're the same value, the ghosts of simultaneous equations start to rise up. And what they'll do is they go, oh, you could substitute, you can cancel all this crap out that I don't know. All right, beautiful. So you're like, oh, I can use all of my methods stuff. And I'm pretty sure you did simultaneous equations year 10 anyways, it's not even methods. Right? So you notice that if you could knock out the KQ squareds, you'd be left with F equated to some number. How neat is that? So that's what I've done here. Okay, equate and solve for F. So you equate and solve for F and you get an actual answer. Find the size of the force that charge C exerts on B. That's the force of charge A and B on, C on A. Okay. Then in question 35, it just asks you to find the sum. Yeah, that's just a vector addition. I don't need to go into that. And what is the angle? Bang, again, just use a little bit of trig, throw that in there, mix it up. Moving on, too easy, same stuff as before. Oh, that's the bottom of the first section. You see the scanner over at the photocopier wouldn't let me scan the whole document at once. It's just way too big to handle. So I had to split it into 2 documents, questions 1 to 38, and then 39 to 60 or 68, I think. Yeah, anyway. Cool. So here is the other document. So these are all available to you, you know, uploaded into the ether. All right, so I had a look at this one here. That was, again, there's a lot of description in how to do it if you're getting stuck. Again, this is another one of these fractiony ones. Didn't think there was worth doing that. So here we go. In terms of, why did I highlight 42? In terms of F, what is the magnitude of the resultant force on plus Q due to both plus big Q and plus 3 big Q? So what did I do? Oh, in terms of F. See, I hate it when... Okay. If you follow this all the way down, you find that you have the 2 different forces in terms of F, okay? The little pink line here is 3/4 of F if the green line is F. And again, the mathematics is exactly the same as things that we've done several times already. right there. And it just becomes a question of fractions. Fractions and then a little bit of Pythagoras once you've isolated what your two f values are, adding them up with Pythagoras and not getting freaked out by the fractions to get 5f on 4, which is the correct answer. Okay, so yeah, I don't want to go through all of that. It's just, you can see it there. I've put tons of detail in there. All right, so 43, 44. Okay, this was an interesting question in logic as well. Okay, so here we have, this is interesting because the diagram below shows the paths of two positively charged particles that move through electric fields between two parallel plates. Ignore the effects of gravity in this question. Awesome. So, two particles enter this electric field. Now you can see that they go, and we're ignoring gravity, so they're arcing towards this plate. So I'm going to guess that these particles are positive since they are seeking the negative plate. Okay? The two particles enter the electric field with the same velocity which was initially perpendicular to the electric field. The positive charge on each particle was the same magnitude. So both particles have the same amount of charge. Okay, but they've behaved differently. So you're going to say to yourself, well, why? What is different about them? They have the same charge, they've been fired in with the same amount of energy, yet one of them landed earlier than the other. Okay? So there's something different about them. Determine which particle, 1 or 2, had the greater mass and justify your answer. So in other words, you can't get away with guessing. It's 3 marks and it's a 2-year-old question. So you can get something like this on an exam if they're being a little bit mean, right? So what is the force acting on both particles? All right. The force acting on both particles is F equals QE, because it's the particles, they both have the same charge and they are entered a field which is exactly the same, exactly the same electric field. So they're experiencing the same force down, both of them, okay? Yet one of them fell faster than the other, okay? So this was where I thought it was really neat, linking a couple of ideas. The force they experience, because they're both experiencing a force, you have to understand that they are experiencing an acceleration as well. Okay, so what they are doing is they're experiencing a different acceleration because something about them is different. So F equals ma, solved for acceleration, tells us that if one of them accelerated down ahead of the other, then one of them had a greater acceleration than the other because they had a different mass. All right? So now what you do is you ask yourself, for the one to get to the ground first, had to have what? How does it work? So for this particle here, it says the particle with the greater acceleration, all right, is the one with the smaller mass. See, for acceleration to be big, the mass of one of the particles has to be smaller, and therefore it gets to the ground faster. Okay, so what that gives us is the mass of particle 2 has to be smaller. Okay, the mass of particle 2 has to be smaller because it accelerates harder towards the plane. All right? The mass of particle 1 is greater. So that's that's the justification of the answer using a proper mathematical treatment of it. All right? So I like that question because you really had to do a lot more for it than you would first imagine. Okay, this one's too simple, another easy. Okay. All right, let's have a quick look at number 47. A helium nucleus contains 2 protons and 2 neutrons, and may be pictured at a particular moment as shown below. So here you've got 2 neutrons, 2 protons. This is the helium nucleus, okay? All right, the protons, P1 and P2, each with a charge of 1.6 by 10 to the negative 19 coulombs, plus, because they're positive, separated by 1.4 by 10 to the negative 15 meters, and the electrostatic force between them, in other words, the force of repulsion that they feel, that comes from KQQ on R squared, is 118 newtons. All right. What is the magnitude of the electrostatic force between the neutron, N1, and the proton, P1? I wanted to mention this because the first particle ever discovered, we knew about atoms and lots of theories about them, but we had to figure out what they looked like and how they behaved, what the charge, what their mass of the different parts were, and we're still learning about them even now. But one of the first things we figured out was the electron. The electron was the easiest to find. Why? Because it's negatively charged, which means you can mess with it with electric and magnetic fields, and it is very easy to rip off an atom, so we found it really fast. Not long after, the proton buried in that nucleus was found. Again, relatively easily because it's charged, it's big, you can do stuff to it, right? The neutron came much later. We found the neutron much later because we knew it had to be there because atoms just wouldn't seem to mathematically work if it wasn't there, so they had to go through and look for it. It's really hard to find an object that has no charge, okay, because it's got mass, so you can do things with it, but when it's really, really tiny and has no charge, you can't see it. You can detect that it's there because of its mass, but you can't play with it, you can't move it around, you can't do very much with it. So the neutron took a really long time to find. So that kind of, if you understand that, it took a long time to find because it's not charged. If you understand that, then the answer to this question makes more sense. There is no electrostatic force as the neutron has no charge, all right? So there is an electrostatic force between these two guys because they're charged, but there is nothing between these two. These two are they may as well just be points in space. Electric fields act on charges, on electric charges. They don't act on just anything, okay? Even though when dust particles stick to fan blades, it's because those dust particles have picked up electric charge, and then there's some electrostatic force, and you end up, when you look at your exhaust fan, it's caked in dirt and dust because it's all kind of statically charged from all the motion that happens, all right? Electric forces don't tend to work on objects that have no charge, all right? And the rest of that is all pretty standard and simple. Just follow it. I did put a lot of detail in these answers. Again, here's another one as above. Same thing. 53. Okay. A simplified setup. We're nearly there. Question 53. A simplified setup for an electron gun is shown below. It contains a high voltage source. In normal operation, electrons emerge from the gun, accelerate towards the anode, and are fired out, okay? So this is the electron gun. Now out here you might end up with plates and all sorts of other apparatus to then pick up those electrons and muck around with them. This is essentially what happened in old school TVs. The old-fashioned televisions had an electron gun and big coils of copper wire around the stream, manipulating that stream to strafe across the inside of the screen, and that would illuminate the screen, okay? So we've been using electron guns and the whole idea of electrons for a really long time, and current TVs don't need them anymore and don't use that sort of technology anymore. Okay, so calculate the velocity for electrons of energy 5 kiloelectron volts. That's why I chose this question, because it makes reference to the non-SI description of energy. Okay, so you can see that whole apparatus there is utterly useless. It doesn't really show anything. They're just trying to make it more real world. Calculate the velocity of any electron that's picked up 5 kiloelectron volts of energy. So what does that mean? Well, 5 kiloelectron volts is the same as 5,000 electron volts. In joules, this is 5,000 times 1.6 by 10 to the negative 19, which is 1.8 by 10 to the negative 16 joules of energy. That's how much energy the accelerating field has given each electron. Now, once you know how much energy it's got, we can equate that to its kinetic energy. And so this is really typically a very simple question, but I just wanted to make that link between kilo electron volts and some velocity at the bottom once you've solved for velocity. Okay? So you end up with the actual speed of the electron. Okay? So, nice and easy question, but just wanted to make sure that part was very clear. Alright, over here, the heated filament of a cathode ray tube. So there's the heated element. Here you've got an anode. Alright, so you pump electricity into this metal. Electrons rip off, they're negatively charged, so you give them somewhere to go. The anode, so you positively charge that piece of metal there, and the electrons jump off here and then shoot through here. And they come through and come out nice and straight, and then once they hit a space which is filled with an electric field, then you can deflect those electrons, you can make them do stuff. And this is essentially what's going on inside an old school TV, like I just mentioned. Alright, now, the electrons start at rest. Okay, so over here, they start at rest. And where are we? The electrons start at rest and reach the anode with a velocity of 6 by 10 to the 7 meters per second. Alright, so they get to the anode at 6 by 10 to the 7 meters per second. What is the value of V? In other words, what voltage gave them that velocity? Okay, so we need to figure out basically, well, how much energy did they get? Let's see what I've done here. EK is equal to QV. So the energy that they've picked up, is due to the charge on the electron and whatever the voltage was that accelerated them. Okay, so let's see, what have I done? mv squared on 2, oh okay, that's right, I forgot. They've given you the velocity of the electron as it gets to the anode, so to here. And they've also given, we know the mass of the electron, that will be on your help sheet anyway. So we know how much kinetic energy they picked up from their trip between the filament and the anode. Alright, and we now equate those two because both of these are equal to work done. We know all of this, we know this because it's an electron, we just need to know this. So we solve for the voltage. And this is 1.02 by 10 to the 4 volts. So 1, 2, 3, 4, so lots of volts. Okay? Alright. The stream of electrons enters a region of uniform electric field E in the space between plane parallel deflection plates separated by a spacing of y meters. The top plate is at a potential of negative 1,000 volts and the bottom plate is a potential of positive 1,000 volts. The magnitude of the electric field is 2 by 10 to the 5 newtons per coulomb. So they've given us E, they've even given us the potential difference. What is the spacing between the plates? The only thing here that can mess with you is if you're not exactly super confident with this kind of science, or what you need to keep in mind that traditionally one plate is often referred to as being at 0 potential and the other plate would be at 1,000 or 5,000 or whatever it is. But what you need to notice here, the important clue here, is that if this is at negative 1,000 and this is at positive 1,000, the potential difference between them is 2,000, okay? So you may not have seen something like this before, okay, because it's like a 47-year-old question, right? But the potential difference that you use to calculate what is essentially a really easy question is 2,000 volts, not 1,000 volts, okay? And that's why it's only worth 1 mark. It's actually a really quick and easy question. All right, what is the acceleration of the electrons in the region between the plates? All right, so the acceleration, you know what the force is. You know what the force is on each electron because you've worked it out. Have you worked it out? Yeah. No, well, you can work it out. See it? So basically, F equals EQ. You know the electric field strength and you know the charge on the electron. Okay. So what we're doing here is equating F equals MA because it's still force with F equals EQ. So we equate these two together because we know we have the electric field. We've got the charge. We know the mass. All right, because it's an electron. So you can solve for the acceleration, all right? So that gives us the acceleration that the electron is experiencing while it's in between those plates by doing that really nice little neat equation, okay? Now, okay, here, there's a lot of writing in here, so I'm not really going to go through it. It's just another one of these plate things. Don't forget, I did a nice little diagram of what a proton and alpha particle is and what the differences are. You know, if this is mass m with charge q, then this is mass 4m with charge 2q. All right, that's important. But the rest of it is really, I think, really well explained how to do the rest. Pretty easy. What else have we got? 61. Again, lots of notes in here. Yeah, this one's hilarious. Question 63 required this amount of work in explaining. And down here, the bit that's been cut off by the scanner is there is no way this is a 1 mark question. You have to do like all of this to get to it. I don't know what they were thinking. 1975, I guess the world was much harder back then. You had to go to like wells to get your water in buckets and things. I don't remember. Question 64. Question 64, refer to the setup in question 60, which is that. Okay. Well, travelling between the plates, the path of the electron is... Oh, I do like this question. This really is an important question because of something that it links to in future work, okay? Magnetic fields, future work, not that far in the future, all right? So basically, the force acting on a particle shooting through a magnetic field is always down, okay? So, what does that remind you of? Okay? What does that remind you of? If a force on an object that's moving is always down, what is its path? What path does it follow? Does it follow a circular path? Does it follow a parabolic path, an ellipse, a straight line? What is it, right? This is best linked to projectile motion. In projectile motion, even if you are at the top of a building with a ball in front of your foot and you kick that ball straight out in front of you, it will follow a parabolic curve till it gets to the ground because the force acting on it is always towards the ground. Now, that is different to say, the force of, say, our gravity on a moon or a satellite. The force is always perpendicular to the motion of that object. So the path that it follows is circular, okay? The reason I mention that is because if you fire an electron into an electric field, the force it experiences is straight down towards the positive plate, okay? So its path is parabolic. But what you'll find in the next chapter is if you fire an electron into a magnetic field, you get a different result. A magnetic field applies a force perpendicular to the motion of the electron. What that means is that it follows a circle as it moves in a magnetic field rather than like falling like a parabola. All right, so they are very different and they do get referenced in very recent exams, okay? So this is why I wanted to draw your attention to this particular question, okay? If you're falling under a constant force that is acting down, you follow a parabola. But if you are moving with a constant force that is perpendicular to your motion, like a string on a ball, yeah, spinning around in a circle, that force is always perpendicular to its motion as it moves around, okay? So they're two very different results depending on what they're asking, okay? Keep that one filed away in your head. Now, down here we have Millikan's experiment. Again, you know, little droplets. Another very easy question. You can see that I don't need to really go through that. Question 68. I didn't go over question 68, although I do remember it being kind of a little bit different. Prove that, yeah, no. It's easy. It's easy. You can do that on your own. That's all right. Plus, there's notes there now as well. All right. Well, thank you for. If you got to this part of the video, well done. It's there was a lot to do. Okay. All right. So I'm going to email you guys with a link to this tonight. Once I get done with it on my iMovie, put a little credits on there and stuff. All right. So hope you're having fun with this stuff. Bye for now.